Yeah, thanks a lot. Good morning or good noon for all of you. I have the pleasure to give a short talk about mainly about some results we conducted in TRANS-ALP with the work of my colleagues at ZAMG, Sebastian Lehner and Kathi Enigl, and also contributions of Massimiliano and Alice with discussions and inputs on the work ahead. So we had already heard lots of climate change also from other presentations. I don't want to dig too far in these general remarks because we already heard it. We have different scenarios for our future depending on our CO2 emissions, and these are directly linked to climatic changes which are ahead of us during the next century. There is a really good paper by Kotlaski et al. Who compended all the information on the Alpine region and future changes. And from here, this is this figure here telling the temperature change for 3 different scenarios. So on one hand, we kind of follow the Paris Agreement, RCP 2.6 scenario, and on the other hand, the worst case scenario, RCP 8.5, and you see the different temperature responses until the end of the century, which are, of course, higher in the higher emission scenarios. However, for precipitation, things are not quite as clear. We see bigger changes with higher emission scenarios here again, but more precipitation to be expected in the cold season, winter and spring, and in the summer season. It's not that significant the signal. Only in the worst case scenario we have a kind of a reduction in precipitation. So this as a kind of a teaser and kind of a general remark on climate change in the Alpine regions. However, we are interested here in the changes of high impact events, as we call it, under climate change. And this is a topic we tackled in TRANS-ALP and which I want to bring you further. So what data did we use? We have already heard it by the talk of Alice. We have a damage data. We have the impacts of climate change. We related those observed impacts to meteorological forcing by using observational data like from the Austrian side, the Spartacus data set, which is an observational gridded data set, and the data set conducted of EURAC for the Italian side. We also use reanalysis data, and we also use global climate model data, scenario data, under 2 different emission scenarios. On one hand, the kind of a Paris Agreement scenario, so this SSP 1.26, this kind of Paris Agreement, and then the business as usual scenario following kind of an emission pathway we tracked during the last decades, which we want to, if we track this further, we will end up in this scenario. We don't use just one global model, we use an ensemble of global models, which has 13 members to assess the spread of the models and to some extent the uncertainties afflicted to these projections. What is our methods and workflow? Well, first of all, it starts with the extreme event detection, where Alice already told you something about. And the next step for us was a kind of a weather type classification. I will come back to that later on. And then determination of this high impact weather type. So looking for signatures in the atmosphere that cause high impact events. And then to assess the future changes of these high impact weather types to changes in the frequency and also in the intensity of the precipitation of these weather types. So what is a weather type classification? This is a statistical method to somehow relate the large scale atmospheric field to distinguishable classes. You have here, just for an example, this is not that we used here in the TRANS-ALP project, 8 different patterns of sea level pressure distributions across Europe. And you see these blue areas are some kind of the low pressure areas. The red ones are those of the high pressure areas. And you see there are the variations. So the high and the low pressure system are not always in the same place. And you can use these patterns and assign each day of your sequence to a certain weather type. And this is what we did. There are tremendous numbers of different classification schemes. we use GWT18, which is it's tested. Swiss colleagues did this once. They have tested for the Alpine region different classification schemes, and this one is one of the best performing ones among others. But it's also very easy to use, and we chose to use this. And this classification scheme gives you essentially 18 classes of weather patterns. So each day from our time series from 1915 onwards is assigned to a certain weather type. So how do we use this with TRANS-ALP? So we identify high impact weather types by intersecting them with our event database. As you have also heard from Alice before, we detected by different methods extreme events in South Tyrol, Trentino, and Austria. And this is the list of the most extreme ones here with the precipitation sums in this columns. And for this, we assigned these from these 18 types. We assigned the weather types, and this is the count here. You see on the x-axis these 18 classes of different weather types, and on the y-axis the count of these individual events. And what sticks out is that 2 to 3 weather types are very much related to these extreme events, and this was the thing to assess this further. On the right side, you see just the sea level pressure distribution of this. This is more for the meteorological affinity people here inside, but it's essentially these 6 classes which are related to the most extreme events in the Alpine region of our observational. So we had a very close look to the VIA event, because we learned that this event was really impactful and really a benchmark event for civil protection also. And we looked at this in more detail. So what was going on at VIA? So this mess of colors and lines is essentially a weather map, which weather forecasters use for the weather forecasts. And this is essentially the Atlantic sector and Europe. But to help you a bit out, here are the Alps at the center of the picture. And here are depicted low pressure and high pressure systems. So the centers of these systems are indicated here. And what we saw with VIA, we have this low pressure system over the Western Mediterranean, which produces this kind of southerly flow towards the Alps. And this is a situation which can cause huge amounts of precipitation, particularly if the Mediterranean Sea is warm and much moisture can evaporate and bring very much moisture towards the Alps. And this is also a weather situation which is depicted by this type 7, which we have seen before, this weather type 7. And this is kind of a benchmark weather type to have a closer look to, and what we also did within TRANS-ALP. So what we did then is use this information and transfer it to the climate scenarios. This means we took the climate scenario data, the sea level pressure of the global climate models under different emission scenarios, and looked for the signatures and the changes of the given weather types. And what we came up here is these graphs here, which show the changes in the frequency of occurrence of certain weather types. Again, we have here on the x-axis these 18 classes of weather types. On the y-axis, the change in percent. And on the left-hand side, we have the Paris Agreement scenario. And on the right-hand side, the business as usual scenario. And what you see, some weather types show an increase in frequency and some show a decrease. So there's a change going on in the different weather situations here. And what is interesting, is that the type 7, which we assigned to as the VIA type kind of weather pattern, shows an increase in both scenarios in frequency. So this means we expect for the future, and this is rather robust, the signal, because most of the models and the spread is depicting the climate model runs is showing in the same direction. So we are rather confident that these VIA-like storms are becoming more frequent in the future, because we also have a rather high model agreement for this weather type. What we also see is that we have more moderate changes for the Paris Agreement scenario, and for the higher emission scenario, we have even a higher change in the frequency, which is interesting because it somehow depicts that there is some dependency on the emission pathway, even on the distribution of these weather types. So what we did also was to look at these weather types and the related precipitation intensity and the related changes in the future. And what we see here, this is the same graph, but now for the precipitation intensity. We see here that this model agreement is not so high because precipitation is a very difficult to model parameter, particularly in the Alpine region. However, what we see is again that for this type 7, the wire-like type, we have an increase in precipitation intensity. This means that wire-like storms are becoming more intense. And we have, again, quite a high model agreement, particularly with the higher emissions scenario. And we have moderate changes within the Paris Agreement scenario and larger changes in the business as usual scenario. This is among many other things we came up in TRANS-ALP, but I think this is a very important and also illustrative result here. And yeah, to conclude, so especially wire-like conditions show substantially increases in the frequency of occurrence and also in the intensity of the precipitation. Climate models do very well agree on this statement. Other high impact weather types also show some increases in frequency and intensity, but the spreads are larger. So there is more uncertainty on this one. And in general, we have a stronger signal with higher emissions. However, uncertainties in climate projections still prevail. Particularly for the Alpine region, it is really tricky to model precipitation well, and there are also other things going on with the wind speed, and we have really dig more into this topic from observational side and also modeling side to make our statements even more robust. However, this intensification of precipitation is rather likely, and we also saw it in the presentations before. These are things that might happen, and it's also particularly for this region, we are talking here to have this weather type related side of things, because in the Alpine region, we have very small scale differences in the outcome and in the relation to atmospheric circulation and related extreme events and impacts. And with this, I'd like to thank you very much for your attention, and I'm open for any questions. Thank you very much.
Very much, Klaus. Any question, Mark?
Yeah, thanks, Klaus. Maybe one question: if you are aware of any climate attribution studies on the wire storms? I mean, since it was a very, let's say, exceptional event, and I heard that the Mediterranean sea surface temperature was far above average. Yeah, are you aware of any?
I'm not aware of a attribution study which might exist or not. However, the wire event was 2018, I think, and it was only in recent years when the attribution really started to kick off with this kind of event triggering analysis we have. So in the last 2 years, these things are happening, and I'm not aware that this was done for the wire event, I think.
And your expectation would be, so is there a climate change attribution already, or?
Sorry?
And what would be your personal assessment?
Yeah, I think it would be interesting, and these studies are to some extent done already, looking at higher temperatures of the Mediterranean Sea, and what is the impact on extreme precipitation. This is already done. I think we have to look more carefully on the specific weather situation for the region, because as I said, in the Alpine region, the meteorological situation or triggers are rather different, and is regionally rather fast changing, you know. So you have to specifically pick your events, your region you want to analyze, and then specifically look at the scenarios and the, for example, weather situations and so on. But it's just one step or one approach to go, which we thought was useful, but there's surely others.
Thank you.
Yeah, thank you very much for the talk. I saw recently a presentation from a colleague of yours who kind of said that the models point to a shift of like storm events, like also high wind impact events like Vaya, more to the north, like that, like those maybe storms will move higher in latitude, and countries like Sweden or Norway might be more affected than, for example, Austria. Do you know something about this? For me, from a forester perspective, was like, oh yes, great, because especially the wind impact. I mean, Vaya devastated like a lot of forested land.
The thing is, we already see some kind of a bit of a shift of this polar front and the jet stream towards the north, which is an effect of the general warming. However, to say, oh, we are safe off then if it's moving up to the north, it's not the case, because these changes are so small. And when you see these weather maps, these huge swings of the atmosphere and the jet stream, the Alpine region will still be in the region of big storms to come. This kind of very subtle movements of the polar front won't affect the Alpine region that much, at least not in the season where these storms occur in winter, spring, and autumn. It has more an impact perhaps in decades ahead for the summer climate, when the tropical high pressure belt is moving northwards.
Yeah. So in East Tyrol, and maybe, or for sure in Italy too, they are still handling the problems after Vaya 4 years later. And as I've heard, the real bark beetle problems just came up the last summer. So based on your conclusions, could you tell a practitioner that 2018 event was just the beginning of what comes next?
That's that's tricky, because giving all this analysis here and changes in frequency and so on, speaking about just the beginning is you have to have the context, and we just have this very small amount of the climatological observational record and room space for extreme events, and we don't know what happened in the past. So it might happen in the past, which is likely, but we to somehow tweak the likelihood of this kind of events. Speaking of, this is just the beginning, might raise the expectation that we have it all 2 or 5 years, which might not be the case, but we have to be prepared that these kind of events will be more frequent to some extent, and also more intense. Yeah.
So they shouldn't be surprised, kind of.
They shouldn't be surprised. Yes, of course. Yeah. It's not that the thing that this is not happening the next 1,000 years. I would expect that we see some kind of this, although it's very unlikely somehow in the next decades. But I just can't. I don't have this ability to predict.